During this lesson, we're going to learn the foundations of dynamic routing. Okay, so for the agenda, we're going to be discussing the benefits of dynamic routing. And then we're going to learn about the different types of routing protocols and how we can classify routing protocols. Afterwards, we're going to learn OSPF protocol. And really, this course only focuses on OSPF as the only dynamic routing protocol we're going to be using. For more protocols, you're welcome to join us on the upcoming series on JNCIS ENT. Then finally, we're going to learn basic OSPF configuration and verification as a lab, of course. So we learned in our previous lesson about static routing and how it might help or it might provide routing information for diverse situations. But what are the benefits of dynamic routing? You guys remember during the last lesson I said if we're talking about a routed environment which is medium to large size, we don't really want to run static routing, but rather dynamic routing. Remember I told you that? Well, here's why. As a first point, routing protocols have the capability to react dynamically to topology changes. Okay, this is not the same case as in static routing. Static routing does not have that intelligence. Then configuration is also less involved than static routing. Once you configure the routing protocol and include your statements that you require, it pretty much self-configures when it comes to changes and when it comes to adapting to different situations. Of course, you need to give it maintenance if things changes, policies change, etc. But it's less involved in the sense that once it's activated and the topology remains stable, you got nothing to do. Then it's critical to have for scaling a network, that's for sure. That same dynamic characteristic that we are highlighting here is the reason why scaling a network with a dynamic routing protocol is much easier than with static routing. Also, migrations and device additions are managed more easily with dynamic routing protocols. Okay, having said that, let's discuss about what types of routing protocols there are, or actually how can we take the existing routing protocols and classify them. The first way to classify them I'm going to talk about is depending on the routing scope, meaning whether the routing protocol is routing across autonomous systems, okay, or if it's routing internally across networks. These concepts might sound a bit foreign for you, but I'm going to explain it. There is only one protocol which routes across autonomous systems, and it's called BGP. Okay. In this case, it's also called eBGP, as you can see there on the slide, as standing for external BGP, but the protocol itself is BGP. eBGP is like a flavor from BGP. Okay. It might seem confusing because now I'm talking two things and there's yet a third one, right? In parentheses there is EGP. Oh my god, what's that all about? Okay, that's the classification. EGP meaning external gateway protocol. And the easy part of this, although it's many names to consider, but the easy part of this is that there is only one protocol which is an EGP, and it's called BGP. Okay. What you see on the slide, those AS-65000 and 6501, those are autonomous systems, and just as the companies and entities requesting IP address blocks from IANA, they can get IP addresses assigned for their own business. Just in the same manner, there are autonomous system numbers available for entities which are large enough to require their own autonomous system. Okay, so autonomous systems are a unique identifier for networks that are under the same administration, and they are large enough to advertise this identifier to the internet, so that routers seeking to communicate with this autonomous system can find it. And then the routers enabled on the internet with BGP are able to route across autonomous systems. If you talk about OSPF, for example, and there you have it here on the right hand, on the cloud at the right hand, inside the cloud, it's running OSPF. OSPF, you can do a lot with it. You can tell it how to reach X and Y networks, even public networks, but you cannot tell OSPF about autonomous systems because it does not route across autonomous systems. It routes across networks. You see the difference? It's different scope and different criteria used. The same happens with the one at the left, ISIS or ISIS. So this is the first classification. There's only one protocol routing across autonomous systems. It's called BGP. And in the topology there, you can see it's running between the two different autonomous systems interconnected here, okay, in those 4 edge routers. And then internally, for the purposes of traffic routing internally to each network, one network is running ISIS for that purpose, and the other one is running OSPF for that purpose, okay? We're not gonna get into more details about this. Again, as I've been saying, and maybe advertising, there's gonna be a full course on JNCIS ENT in which we will delve into each of these protocols and we will learn each of them. So I hope this creates an expectation, and I hope you will join us on that course as well. Okay. Okay, this is just showing that the internal gateway protocols are running across those interfaces which are internal to each cloud. Now there's a second classification of routing protocols, and this one is based on how the router perceives its own environment, and hence how this affects the routing decision that it makes. Okay, so we have two classic examples on screen. At the left we have RIP, which is an IGP. I'm just putting the previous classification so you remember. IGP is an internal gateway protocol versus EGP, external gateway protocol. So the RIP IGP is running on the left hand side cloud. The OSPF IGP is running on the right hand cloud, okay, inside of it. Now, a distance vector routing protocol, it's said that it routes by rumor. What does that mean? It just tells the others what the others tell it, and that's it. Okay? Oh, I heard from this neighbor, which is directly connected. I heard it that he has access to this network. Oh, really? Yeah. Here it is. Take it. And then to the other one, it says the same about the other directly connect network. Neighbor. So its knowledge is limited only to those directly connected neighbors. And as you can see here, this is what the router thinks. Well, this is me, and then my neighbors are the two directly connected ones. As you can see, there are other two neighbors. The external routers on their internal interfaces, they are also part of that topology, but the router does not consider them its neighbors because they are not directly connected. So whatever information from those routers or from the routes which those routers are able to reach, it's only gonna be able to get it via one of its directly connected neighbors, and that's it. Now, how can that be different? Well, OSPF. Take OSPF for example. The router, in this case the router at the center, considers itself, and it considers each and every router running OSPF in the topology as part of its neighborhood. Okay? It is conscious of each and every router that comprises its neighborhood. If there were more routers even connected to the other routers it connects to, and they run OSPF, it would know about them as well. Because link state routing protocols build a topology database which allowed them to keep track of each and every neighbor that they have. Okay? And it's the state of its links. And when we talk about the state of its links, of course, it's super important because the links of the router determine what networks that it has access to, of course. And if a link is down, then it might lose access to that network and so on. So that's why it's called a link state protocol, because it tracks the state of the links. But moreover, it also knows, it has a full view of its neighborhood. So it's able to make more sophisticated computations, faster and more efficient decisions than a distance vector routing protocol, which is the reason why very few people nowadays use RIP or a distance vector routing protocol such as IGRP, for example. Very few people will do that, and best practice is to use link state. Okay. So OSPF. Let's talk about it, because OSPF is the routing protocol that we will learn according to the JNCIA Junos curricula, which we're following. OSPF is a link state protocol. It advertises the state of its interfaces to other routers, and it also receives information from them to build a link state database. This link state database I'm talking about is the one that allows the router to be conscious of all of its topology. So it's a very important device or tool inside OSPF. Okay. And then how does OSPF make decisions? It uses a metric called cost to determine the shortest path to a destination. Now, when I'm talking about a shortest path, I am not talking about how many links or how many hops are in between it and a destination. That would be a logic of the distance vector protocols. And OSPF is not a distance vector, it's a link state protocol. So the logic it uses is each link has a cost. When we add up the cost to a destination of all the links in between, the lower the better. Then all OSPF routers must connect to area 0. This is a requirement, and there are some ways that this can be worked around for some scenarios, but the default and the best practice is OSPF routers must always connect to area 0. Okay, so let's see how cost works as a basic metric to determine the shortest path to a certain destination. OSPF will assign costs to its interfaces, and depending on the interface, a calculation is going to be made to determine the cost of each link to a destination. It's also important for you to know that you can influence these calculations directly by tweaking the formula, and also you can influence by setting up manual costs, so it's very flexible. For the time being, I'm interested that you understand that the metric OSPF uses is cumulative, and it's obtained by adding up the costs of each link. So, as I said before, OSPF runs the Dijkstra algorithm, and what it does is, in a redundant topology like the one you see here, OSPF, it's going to determine what is the shortest path based on cost. So it's going to be an operation similar to pruning branches of a tree. Okay, similar to pruning branches of a tree. And this is what the algorithm does. It creates a tree of indicating the shortest path to a destination. So you can see different values from the links. We will see how we eliminate links based on the cost. For example, see this, it might seem counterintuitive, but it's eliminating the link with cost 1. Well, because in that path, the following link has a cost of 10. So 10 plus 1 is 11, right? See, in the lower path, the first link has a cost of 5, which is higher than 1. But then the additional link, the link that follows, has a cost of 1. So 5 plus 1 is 6. So by eliminating the upper path and going through the lower path, we're saving 5 values of the cost, for so to speak. So because 11 is higher than 6, we're going to prefer the path which equals to 6. Now, the the path is just halfways here, right? Because the idea is to go to reach the networks behind router B. So you see we're eliminating this link which has a value of 5, a cost of 5, and we're eliminating the following link which has a cost of 100, and we're preferring the path, the upper path in this case, because it contains a value of 5 in the first link and a value of 10 in the second link, so it's 15 versus 105. Okay, so in total, this path OSPF has chosen is the shortest path from router A to router B. And in very simple terms, this is the logic behind OSPF operation. Of course, there's more to it and to its calculations, but that is not a topic that concerns this particular curricula. For now, it is important that you understand the basic operation based on cost. So the total cost of the preferred path is 21 in this case. Now let's talk about the areas. How does it work with areas? So as you can see, here is area 0. Area 0 is also known as the backbone area. The reason why it's known as the backbone area is because OSPF protocol enforces hierarchical routed network design. So every area needs to connect to the backbone. The backbone will do the inter-area forwarding, and each area can communicate with each other through the backbone area. That is the initial logic. Now, it is also possible to have entire networks on area 0, but those have to be small size networks typically. Okay. Now see, in this case we're introducing area 2. Area 2 is perfectly fine the way it is defined right here, because it connects to router 2, and router 2 is part of area 0. So in this sense, router 2 will have two interfaces, the ones that go through to router 1 and router 4, two interfacing area 0, and one interface in area 2, okay, connecting to router 5. This is correct. This is good design. What is not good design, what is not even allowed by OSPF, meaning it's not gonna work, is this. So we have area 51, yeah, area 51 connected to area 2, okay, but it's not connected to area 0, so OSPF is not going to accept this. It's not going to even take the information coming from area 51 because it has not a direct connection to area 0. If we remove it from here and we add it to router 3, for example, now router 3 has an interface in area 51 and two interfaces in area 0, that would be considered good design, and OSPF is going to work and create calculations and share information across areas in this second scenario. Okay, so now that we've got our feet wet concerning OSPF's operation and what is the use of a dynamic routing protocol, specifically a link state routing protocol such as OSPF, let's just go ahead and put it in practice. And if you notice, this is the topology diagram of the lab we're going to be doing. And if you notice, this is the exact same topology as we had for our previous lesson, okay, as we had for our previous lesson on static routing. What's the difference? The difference is I am going to be making changes, okay? The goal is the same. Loopback 0 behind router A, which stands for 10.10.10.1/24, will need to communicate with loopback 0.1 behind router B VI2 with IP address 10.20.20.1/24. That's the objective. It's the same thing. However, I wanted to keep it the same because I want you to see how dramatic the difference in configuration and workload and simplicity is when we're doing this via static routing means than when we're doing this via OSPF means. Okay, it's so much simpler, and you will see you will see also in the duration of this lab it's going to be like 1 2 3, there you go. So let's go ahead and make sure we remove any static configuration first, and then let's just configure OSPF, basic OSPF, single area OSPF, meaning everything in area 0. Now, before going there, I just want to say something. If you're not looking at the videos in order, you might find the example I'm about to give overly simplistic, and you might want to go ahead and review the static routing video, which comes before this one in the playlist, just for you to see how dramatic the change is from configuring this topology with static routing than OSPF. In any case, I'm always attaching the configurations so you can simply load them and modify them. So it's your pick, but you'll make the most out of it if you look at the previous video first. Make sense? We have a deal? All right, let's move on. So I'm in router A right now, and I want to get rid of everything static. So let me see what exactly is the static routing in this router. So I'm gonna do show pipe match static, and then I'm gonna do a display set. Okay, what do we have here? We have set routing option static route. Well, the routes to 10.20.20.0/24, next hop and qualified next hop. Okay, and then the resolve option, and then an actual route to an indirect next hop. Okay, that's what we have. Now I can delete statement by statement, or I can do it even simpler and do the following: delete routing options static. This is the same command as before. There's nothing there. That's it. Very simple. Because in this case, this is a lab, of course. You're gonna think it twice before doing this in a production router, because this is gonna delete every single static route configuration there is. So for this scenario, it's okay. So let's just commit it. Commit comment and jvar deleted static. All right. Now I'm gonna move to router B, and in consequence to router B, and also router B-VI1 and router B-VI2. So it's 3 routers in one, if you remember from the past lesson. But since everything's physically in router B, it's gonna be simple because we're gonna do it from the same device. So I'm gonna do the same thing, show match static display set. You're gonna notice there's more configuration here because we have static routes in every routing instance. Okay, so we want to make sure that we delete the statics in routing options, just like we did with router A, but we also go to each and every one of the 2 routing instances, it's only 2 of them, and delete the routing option static from them as well. Okay, so we want to do that. We're gonna leave this completely lacking of routing information so that OSPF can take care of it. So delete routing options static, first statement. Delete routing instances router B-VI1 routing options static, and then the same thing but with router B-VI2, and there we go. Now let's do the same command as before. Show match static display set, nothing's there. Amazing. So commit comment jvar, oh that's kvar, jvar deleted all statics, and voila. So let's allow it to commit, and then we can move on with our OSPF configuration. Good. Let me just show you how we're really without any routing information to reach the opposite LAN. So run show route 10.20.20.1. Okay, well that's local. That's my bad because this is router B. I meant to say 10.10.10.1. There we go. There's no route. Okay, there's no route in any of the routing tables, by the way. Okay, so that might be a problem, right? If we do just a plain show route, what we're gonna see is simply the directly connected networks in each of the different routing tables. So INET at 0, that's our default. Then the directly connected networks there. VI1, the same, directly connected networks. If you refer to the diagram, those are just the point-to-point links. And then just the same in router B, VI2 INET.0. And then we have the IPv6 tables, but we're not even using this in this example. So this is just for you to see that we really are without routing information right now. If you go ahead and you change your cable and you go to router A, do the exact same thing, well, you're going to see the exact same thing as well. So run show route 10.20.20.0, no way. Okay, just a simple plain run show route. Okay, now this shows us the point-to-point links. Remember that we're now running router A with a single routing instance, and then here we see the INET 6.0 for the IPv6 addresses. So this is the state where I want us to be, where we have no routing info. Now let's go back to our diagram for a moment. Okay, remember I told you OSPF is called a link state routing protocol, right? Well, no coincidence. The way we configure OSPF, and really the way OSPF protocol is designed to work, is by advertising its links. What do you mean advertising its links? Well, the router has links, right? It has actual cables, actual connections, not necessarily cables because there might be of a virtual nature, right? But nevertheless, they are links to certain networks. That's the principle. So what we're going to do with OSPF is we're going to tell OSPF, hey, you need to take this interface into consideration, and also this one, and this one, and the other one, okay? So as we include interface into the OSPF process, OSPF is going to take the information of the networks associated with those interfaces and is going to build the topology table that we learned about in the previous slides, and it's going to share that information across all neighbors, and all neighbors should, by requirement of the protocol, have the same view of the topology. So configuring OSPF, as opposed to configuring the static routing examples we learned about on the previous lesson, is so much easier. It's as easy as just declaring the interfaces as part of OSPF and just let it do its magic. So let's just go ahead and go to router 1, sorry, or router A, and declare loopback 00, and declare fast Ethernet 1 and 2, and then we're gonna go to router B and declare all interfaces associated to all instances. Let's just go ahead and do that. Good. So router A, what we're gonna do is this: set protocols. Notice it's not on routing options. It's not set routing options protocols. No. See? No protocols. I'm just clarifying this because it might sound logic to you to think, well, it's routing, right? No. It's set protocols, OSPF. We're going to declare the area we're going to be working on, area 0. Okay? And then we're going to give it interface. And in the case of router A, that would be on interfaces fast Ethernet 001 and 002. Okay, good. That takes care of half of the lab. Well, maybe a third part. So commit comment. OSPF is so much simpler, we're gonna call it. Now, some will argue, of course, this is not the most complex OSPF scenario, right? And I guess we can all agree with that. But my point here is it's so much simpler to configure OSPF than to do everything by statics. Let's go to router B. And so here we're going to be careful with one thing. Router B has 3 routing instances. So we need to create OSPF area 0 process on each of the instances and declare interfaces associated to each of the instances. Okay? So let's go first to the default routing table. So set protocols OSPF area 0, and then interface, and then on router B would be fast Ethernet 001, and then fast Ethernet 003. Okay. Now let's go to router BVI1. set, remember, routing instance, router VVI. It says 1 or 2. 1. And then from here, from inside the instance, we define protocols, OSPF, area 0, interface, and then in this case it will be Fast Ethernet 002 and 006. Make sense? Okay, one more to go. Set routing instances, router BVI2, protocol, OSPF, area 0, interfaces, and in this case, or interface, it's going to be Fast Ethernet 004 and Fast Ethernet 007. Okay, am I missing anything? What do you guys think? Think about it. Let's do a quick show pipe compare. Yeah, we defined protocols OSPF on default routing instance. We defined it on BVI1, BVI2 with its interfaces. Is there anything missing? Yes, there is something missing. I did not declare the loopback interface. And remember, the goal of the scenario is to reach from loopback to loopback. And as a matter of fact, I did not declare it on router A either. I'll have to go there and correct that. Else we're not going to have full route information. So let me go ahead and do this correction real quick. Router loopback 0.1 in here in router B is in the router BVI2 instance. So I'm just recycling the command here with the up arrow, and then just loopback 0.1, and there we go. Show pipe compare. All right, that seems to be really good. Commit comment, JVAR, much simpler with OSPF. Yeah, it seems like I'm in an advertising campaign for OSPF. Okay, if you're using physical devices, you might have noticed your ports are blinking. Well, OSPF is doing its work, and it's negotiating parameters and neighborships, so that's why you see them blinking. It's already acting. But I remember I told you I missed to declare the loopback, so let's do that real quick. Start protocols, OSPF, area 0. That's good as well. It just auto-completed 0.0.0. It's fine. It's the same. Interface, and then LO0. Show pipe compare. Okay, good. Commit comment, JVAR, included loopback. Let's just slide it commit. Okay, you guys ready for the magic? Let's do a run show route here in router 8. Run show route 10.20.20.0. Sure enough, you get two different hops. It's choosing 172.25.30.2 right now, and it is working. It has a route. Okay. Now, what if I wanted to, let's say, access the remote next hops? Remember that, like the next hops of router B and VI1 to VI2, for example. Do we have a route for that? Show route. Oh, sorry, it's a run show route. Run show route 172.25.4.30. Sorry, is that 30.4? I was like, what? That 30.4. Sure enough, OSPF is able to do that without the need of any manual intervention like we had to in the previous exercise. So it's all declared in there. So now let's just ping it. Run, ping 10.20.20.1, and it works. Okay. Let's see what about OSPF neighborships. So run show OSPF neighbors. Okay, I can see here that from the standpoint of router A, I have neighborship with .30.2 on both subnets. Okay, which is it's okay because those are the two routing instances in router B. Now for router B, it's going to show a bit of a more complex topology of neighbors, but because it has different routing instances. So run show OSPF neighbors or OSPF neighbor. Okay, and this is for the default routing instance. If we wanted to see for the other routing instance, we have to specify it, like with everything routing instances, right? Instance router B-VVI1, router B-VVI2, and you can see the neighborship that formed on each routing instance. Okay, remember to always call the routing instance when you want to see routing instance specific info, because by default all commands only apply to the default routing instance.